What's up, guys? I hope you all are doing well. Welcome back to my YouTube channel and welcome back to another YouTube video. So, this is part 5 of the SciPy package within the tutorial series Scientific and Numeric Computing in Python. Now, I should mention, guys, that this is the last video in the entire tutorial series. So, after this, we will have completed a scientific and numeric computing in Python tutorial series. So essentially what this means is that you would have experience in NumPy and SciPy, okay? And the experience that you will have, I would say, falls into the category of intermediate to advanced. So that is good progress. Now, essentially what we will be doing in this last video, as I mentioned in the previous video, is we will be looking at statistics, okay? Statistics, that's available to us from the SciPy module. So we will not be doing anything like I would say difficult in inverted commas. Essentially, this is just us exploring the different kind of stats that we can use to describe the data that we are working with. Now, first things first, I will create a cell here, and essentially what we will be looking at is basically statistic functions. That's what we are looking at. So I should mention to you, right, in SciPy, there's more than 60 plus, statistical functions that we have available to us. Now, if you are a new a learner to SciPy especially, and you kind of get intimidated by this, now it can at times be overwhelming, okay, to digest all of these functions, especially if you are just, looking to just learn SciPy out of curiosity, okay, just to expand on your knowledge. So you may not know where to start with these functions. So essentially, the best way to think of all of these functions is that they either describe or they test the samples in the data set. So that's the two main broad categories, okay? Functions either describe the data or they test the data. So that is the two main broad categories. So for example, right, if we have to obtain, say, the frequency or maybe the average, that's the description portions of the data. Now, with regard to tests, there are other features and functions that are basically used to test, or run predictions on the data points itself. So that's the two broad categories. So you see, SciPy itself, it's based on a whole lot of math. Okay, there's a lot of maths and mathematical concepts that kind of backs up the use of the package. Now, for this reason, okay, we have this sub package called stats. That's the sub package within the SciPy module. So stats is what we will be using or looking at. Now you see, within the stats package, there are several functions that we have access to. So I will just be demonstrating just a few useful ones that I'd like to, go through with you, just to give you a hands-on experience with those functions. So that's what we will be doing now. So go ahead, let's import our NumPy package first. Import NumPy as np. Next, I will do from NumPy, or rather from SciPy, import stats. So that's what we are doing there. Now, for this, we will require some sample data to work with. Okay, so let's generate. We'd like to have 100 elements. So what we will do is we'll utilize a random seed for this generation. So what we can do is numpy.random.seed, and let's set this to 42. So essentially, if you are new to this kind of function, random.seed, specifically the seed portion, so right, that numpy.random is used to generate random values. So essentially, think of it such way: without the seed, okay, without setting a seed, the numbers that are randomly generated will be different each time you run the script. But by having a seed that is fixed, it causes the randomly generated numbers to be the same okay, irrespective of how many times you run the script, it will be the same. So now what we can do after setting a random seed, we can do, let's call the sample, since that is the sample of our data set, and we can say numpy.random.randn, and within this I can pass 100. So it will generate 100 numbers for me between the predefined range of random.randn, and having a random seed will ensure that those numbers are the same every time I run the script. Now the reason why I am setting a random seed is because, think about it, we are going to be working with stats, and essentially I would like us all to have the same output. So that's why I set a random seed. And let's proceed further now. So the first and foremost thing that I'd like to demonstrate how you can do is to actually test the null hypothesis. So the way in which we can do this is to utilize the normal test function that's available to us from the stats sub package. So the name of the function we are working with is normal test. This is one of those testing functions. So let's try that out. So what we can do is, let's call this out is equals to stats dot normal test, and within this I pass in my population of data. So let's pass in sample. And after this, now what I'd like you to basically see is that as we go through this tutorial, what you'll see is that I kind of make the output much more, I would say, explanatory and kind of readable for us. Because what you will find, guys, is that majority of the stats modules functions, they output a tuple of values, okay? And because of the fact that it is a tuple, we can index this tuple to obtain the necessary values we'd like, and maybe next to a print statement that prints out a description, okay? So what I mean is that, see, if you view the output of the out variable, so the normal test, the output of normal test is, as you see, we have a normal test result, we have statistic and p-value. Okay, so to make this more explanatory, as I'm saying, what I will do is I will give us a little printout. So normal test output, and essentially the first value we see is the z-score, and the second value is the p-value. Okay, z-score or z-statistic and the p-value. So let me actually print that out for us. So z-score, and this will be, let's string, since we are working with indices, so we'll string the output and the first value, which is 0. So I will copy this for us, and the next one is the p value. Okay, so that's good, and this will just change to 1. So as you guys can see, now we do have the output being much more readable for us. So it is nice to have in the script itself. So when you look back at this SciPy script, you'll have everything kind of organized for yourself. So that's the first test function we looked at, normal test. Now what I'd like to actually demonstrate to you is the KS test. KS test now is basically the Kolmogorov. I may be saying that wrong, but you get the idea. So it's the, let me add this as a comment. So it's the Kolmogorov-Smirnov, that's how I pronounce it, and it's basically this test is one for to test basically when you have a distribution or a function or a graph or gradient or whatever. Doing this test on your data would basically test the goodness of the fit you have. Okay, kind of like you can think of it as being like the accuracy of the fit you have. Okay, so what we will do is we will still utilize our sample data, and if you are familiar with the SciPy gives us access to several distributions. Okay, by distributions we mean graphs. What you guys can do, I would like you guys to actually do this, is head over to Google or your search engine of choice and type in Google, search for a list of all supported SciPy distributions with a visualization. Okay, and you will get outputted with a basically a website that contains all the different types of graphs that SciPy allows you to work with. Okay, the reason why I say this is because one of the most important baseline distributions is known as the normal distribution. Okay, and the test we are about to do now, the KS test, it's actually based on the normal distribution. So it utilizes a feature of the normal distribution. So just to give you a bit more insight, let's comment this. The KS test is used to test the goodness of the fit. And what I will say is, below we test our sample data against the normal distribution. D is the KS statistic, and the closer it is to 0, the better the fit. So let's actually code this out now. So what we will do is call this out again. I will create a new cell. So out is equals to stats.kstest, and within this kstest function we need to pass the data definitely. And as you guys can see, we need to pass basically the CDF. Okay, so the CDF is basically our distribution itself. So CDF, if you are wondering, it basically stands for cumulative distribution function. And cumulative distribution function is representing the function of the distribution against which we want to test the data. So as I said in the comment here, we are testing against the normal distribution. So we would essentially set CDF to be equal to a value of norm. Okay, and you guys can Google the appropriate string values for the other distributions. Now that is that. So essentially this is really all we need to do, right? Running this would give us output, and remember the sample data has not changed. So as I told you, we do get tuples, but I'd like to make these tuples much more readable for us. So what I can do is, let me print out a little paragraph of text, just like how we did for the normal test earlier. So what I can do is, let's say KS test output for normal distribution, and below let's actually print the stats itself. So as I told you, D is the KS statistic, right? This first statistic you see here is represented by D. So D, and let's actually place the value of that tuple, the first value in that tuple. So again we will string, I'll copy this, and now we have P value once again, and this will just be 1. So running this gives me a much, I would say, much more logical formatting of the output. Now if you'd like to do another testing, so these are testing functions. They, as we said in the beginning of the tutorial, functions can be categorized broadly into the types that describe your data and in the types that allow you to test your data. This is just us exploring some of those functions that can be used to test the data. Okay, we will look at the description functions afterwards. So for now, one more that I'd like to actually demonstrate to you, is what's known as the Wald distribution. Okay, so that's what we will do now. So I will add that as a comment. testing against the world distribution. Just like how we used KS test and we tested against a normal distribution, there's another distribution which is kind of like a, like a, in inverted commas, defaulted graph that SciPy supports. Okay, this is what we are testing our distribution against. So what we will do is let's use the exact same code. I will just copy this. You guys can copy this since output, as I told you, is very similar in terms of formatting. So all we need to do is change this to WALD, world, and we will change the print statement. So output for, let's say, world distribution. And if I run this, you guys see I do get an output. So that's fine. Now another cell. Now let us actually use, or kind of get an insight into the descriptive functions. Descriptive functions, as implied by the name, they tell us more about the data. Something like counting your data is a descriptive function. Okay, because it describes the data. It describes exactly how many observations. By observations, I mean rows we are working with. Okay, so essentially, in the real world, you will also see that researchers and analysts and so on, they will use descriptive functions for statistical purposes. Okay, descriptive functions help the individual who's working with the data to get a higher level of insight into what they are working with. Okay, now again, these are all coming from the stats package. So you will see stuff, interesting stuff like, suppose you'd see stuff like means, averages, you see kurtosis, variance, and so on. So all of these are descriptive functions. Something like min and max, minimum and maximum, it's a part of descriptive functions. So I will import again just for the sake of formality and just to keep everything in one cell. So from SciPy import, and let's do stats. Now again, we are generating the same data again, so I will just copy this. That's fine, I don't need anything else for now. So what I can do now is play around with this data. Let's play around with this data. The first thing I'd like to view is the harmonic mean. The harmonic mean. So basically what I also have to mention here is that the sample values you are working with have to be greater than 0. Okay, you cannot have values that are less than or equals to 0. So what we will do is output is equals to stats dot h mean. This is the function we utilize for harmonic mean, h mean, and within this we will pass the data itself. And since we need those values that are only greater than 0, what we can do is we can use an indexing technique we learned earlier with NumPy. So let's do sample is greater than 0. So that's fine. Now I will run this. I'll just show you what output looks like, and then we can format this properly. So as you can see, it's just one value because at the end of the day, we only have the harmonic mean. So print the harmonic mean of the data. Yeah, and let's string this. So I actually forgot to add my spaces here as well, so that's fine. Okay, so I've just added those spaces real quickly. Now let's string these values together since we are working with a number. So we will just cast string, and we are stringing out. So that's good. The next interesting one can actually be t-mean. Okay, t-mean is basically it's short for like trimmed mean. So t-mean is equals to trimmed mean. If you are unsure what this kind of means, essentially what it means is it is a mean function. It's an average function, and essentially it's a mean value where values below -1 and above +1 are removed for the mean calculation. So I hope that makes sense. That is a simple comment I just wanted to give you guys. T mean or trimmed mean is the mean value where values below -1 and above +1 are removed for the mean calculation. So that's fine. Now let's actually see how this is done. It is easy. So stats dot t mean, within this sample, and there is a parameter here, limits, and it is defaulted to none, but the actual definition of trimmed mean, t mean, is where -1 and +1 are kind of like your outliers. Everything in between needs to be kept. So essentially what we tend to do is within a tuple, to the limits parameter we'll pass an argument of -1 and +1. So let's do print out. You guys will see it is just a number, a single number, and what we can do is format this. So the trimmed mean, let's string that, and yeah, we have that done. Now that is trimmed mean. Now one more thing that I'd like to also just show you is calculating the skewness of the data. So skewness of the data, you guys know in stats, when the data tends to lean, towards one side more, we say it's left or right skewed, and so on. So it's the exact same concept, but in Python syntax. So output is equals to stats.skew, and these are all built-in functions as part of the SciPy module. Okay, we are just utilizing what's there for us. So let's do out, and now let's format this. I'm just doing it here as well so you guys can see what the output looks like. So print, let's do the skewness of the data, and there we have that. So create another cell. This is the last function that I'd like to show you guys, and after this we will conclude the tutorial. It is kind of like in my personal opinion, this function is one of the most useful ones that's part of the stats module, and is used for describing the data we are working with. So it's a description, a very good and detailed description of the data you are working with. Okay, so it is kind of like a summarization function, right? I will comment this for you guys. So there is a very useful summarization function called describe, and this function provides us with a very good and detailed overview of the data. So really that's what it does, right? This function is good. It gives us kind of like a large tuple with many values, and as always I will make that tuple kind of readable, right? We will perform the necessary indexing to extract the values, and we will print it out with a statement or word to say what it means. So let's actually do that. We will say output is equals to stats.describe, and within this we'll pass the data we are working with. In our case it is sample. So I will run this, right? I want you guys to just have a look at what is outputted by actually spelled describe wrong. So yeah, I want you guys have a look at this, guys. We have this tuple. Okay, as you can tell, there is more than one tuple within this. So we have elements, some elements are tuples themselves, and so on. Now everything kind of has its own keyword, right? But I will now make this much more readable for us. As you guys can see, right, we have knobs, mean, kurtosis, variance, min, max, skewness. So it is kind of detailed. And now let's actually proceed to make this readable, or let's format it in a way that's easy to read. So let's do first things first. Let's take it from the first element till the last. So let's do size of sample. So we are stringing output 0, and as you guys will see, size of sample is 100. So that's what the first one stands for. Now we'll just copy this to save time. After size of sample, we see the min max portion there. So that's a tuple itself. So what we'll say, minimum element in sample, and here we are stringing out. We are stringing out, and there is a tuple within a tuple. So what we will do is 1 or 0. Let's copy paste that, because after that, after the minimum, we see the maximum element. Now this will be 1 and 1. So I will run this so you guys can see how it's shaping to be. So let's paste this again. Mean of the sample data So the mean of the sample data will be basically set to be equals to out and 2, element 2. So 0, that's, as you guys can see, I'm just highlighting it on the screen so you understand. That's 0. This will be 1. And there we have the mean, which is element 2. Right? Python is 0 indexed. Now, going further, let's actually do the variance of the sample data, and here we will string output 3. So let's copy this since it is easier from here onwards. So I'll just change the keyword itself. So the statistics skewness, this will be 4, and lastly we have kurtosis of the sample data will be 5, the final element in that tuple. So this is it. Now when I run this, as you guys can see, instead of reading our output from that initial output, all we did was just format it, right? And it made it much more readable to the human eye. Now, this is the last, I would say, concept or thing that we have done for the tutorial series, Scientific and Numeric Computing in Python. I am actually quite happy because it is kind of like the first, I would say, advanced tutorial series that I have out on the channel. So I hope you guys also enjoyed watching this as much as I enjoyed making this. Okay, it enables me to teach and learn at the same time. Now, before we end, I need to tell you, obviously there are so much more stuff that can be done with SciPy, okay? I mean, with the stats package, all the packages that we looked at and more. There are a lot that exist. So the documentation is always there on, Google and on the web for you to look at and read through. And if you need any assistance, feel free to drop a comment in the description, or drop a comment in the comment section rather. So yeah, with that guys, thanks for watching, thanks for staying till the end of the video. Good luck with your work, and I will see you in the next YouTube video.